Welcome, everybody. Today, we're going to be discussing RDF, RDFS, and some acronyms, basically just the acronyms. And we'll start and proceed just as I described in the title here, beginning with the Resource Description Framework, RDF. What is this? It is part of the semantic web stack, what we call a semantic web stack. It's a stack of like tools, methods, strategies, etc., that help us represent information or encode information on what we call the semantic web. And by that, I just mean something along the lines of ways to connect information to other information on the web and more broadly. It's born out of Tim Berners-Lee's genius insights about, hey, it'd be great if we could like create machine readable connections among all this nonsense that goes around and is sprayed around on the internet. Great idea. How do you do that? First step, with the data interchange format, RDF. RDF, Resource Description Framework, resource, everything that can have a unique identifier, like a page or a place or a person or a dog or products, anything. Description, these are attributes and features or relations among resources. And then framework, a model, languages and syntaxes for those descriptions. That's breaking it down. Now I want to, even here, before we really get into it, I'm going to have to draw a distinction that I want you to keep in mind. It'll help avoid confusion in the future. I see this confused very often. RDF is spoken of in multiple ways in the community. Sometimes people just mean a data model, which is RDF. You could see it in the W3C, the World Wide Web Consortium description of its abstract syntax, just a data model that is based on triples, which provides semantics for distributed web data. It is also spoken of as if it is a vocabulary. You can, for instance, download files called rdf.rdf. And people will say, look, this is RDF. There's a difference between a data model and a vocabulary that implements the data model. You'll have to keep that in mind. Sometimes people mean the data model when they're talking. Sometimes people mean the actual text file on your computer or the vocabulary represented in that. But they are different things. Now, what do I mean by triples? What do I mean by triples? There's Mary and she has a job. She's an executive. Good for her. Subject, predicate, object. This is the building block. Simple building block, triple structure, subject, predicate, object. So they're using predicate in the kind of relational sense. But that's fine. Like it's the link, the edge. Now you can have multiple of these, right? Subject, predicate, objects. It's totally fine. Mary, she's got a job, she's a person, has a degree. And also important to the structures that we represent in RDF, the subject predicates objects with unique identifiers. In this case, uniform resource identifier. So, and they often will start with something like HTTPS : // right? www. Here I just made up one, www.example.com, right? If you look around on like Common Core ontologies, BFO, or anything like that, if you look for like the thing you would use as a computer, if you're a computer to identify the class object, it's going to be an identifier of this sort. Hanging off of that identifier is just like this, in this triple structure form, hanging off of that identifier is going to be object, like the label object, right? Now, some serialization or some RDF exist in serializations that are easier for humans to read than others. But many have been developed owing to many translational needs of users. So now we're getting into the thing you might see on your computer rather than a data model. So instead of talking about like this grand triple structure that you have to use if you're going to abide by the standard, now we're talking about like actually seeing it in practice in a vocabulary. And moreover, now we're talking about seeing it in a vocabulary that's represented in different ways, i.e. serializations. Here's some common ones. One of the earliest ones was called RDF XML because people hate other people, basically. RDF XML, the serialization, XML, incidentally, extensible markup language, very commonly used in the web in the past and to some extent still is. Now, you would see if you're trying to represent like Laurel located in Maryland, which is, you can see right here, I've got like in the tag at the end of the identifier, human readable label. You might see something that looks like this. Gross. Look at that. You got the XML stuff. You got blah, 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 example.com, a description that's about Laurel, a label, Maryland, description. Gross. It also, like, it kind of obscures the triple structure that, for me, I'd like to see. Other examples, JSON LD, easy for folks to read, very widely used in the web. It's now a preferred way to structure data, for instance, in the Google Knowledge Graph. So you know it must be good. If you're looking at the same example, it would look something like this in JSON LD, which gives you a little, like, some clues in more of the triple structure. You've got Laurel located in Maryland, and with a label, with some labels.
So that developed because developers hated OWL, and it gave the IEEE did it so that developers it was a bridge.
I think less OWL. I think XML, RDF XML may have been, like, in my experience, the biggest culprit. Although not to say that developers particularly like OWL. But as far as, like, if you're looking at the structure, like in the graph right here, like in the representation on the file, like this is so much easier to look at than this. And also, like, easier to process in many ways, despite the fact that XML, for whatever reason, has a reputation for being easier to process than other serializations. But my understanding, it may have very well have had something to do with, like, their distaste for OWL, but a lot of the hate, I think, came out of the XML serializations. So in addition to these, there's some others to keep in mind that you might come across in your experience as an ontology engineer, like Turtle. My preferred, because it's so simple. It's a compact serialization of RDF. It's very easy to read, I think. You have, like, you can introduce abbreviations for all that HTTP stuff at the top. And then the triple that you'd be looking for after you introduce your abbreviations just looks very simple. Like, you have Laurel, label, and it's located in Maryland. And then the EX here is just, all that nonsense. RDFS, all that nonsense. But you put the colons there, you can abbreviate it. You don't have to look at all that mess. You see a very clean sort of triple structure. Yeah. In triples is another example you might come across. Very similar to Turtle. Don't get them confused, though. This represents triples as unabbreviated URIs enclosed in angle brackets and strings and quotes. Again, very simple or similar. This is something you might see in triples format. You have Laurel located in Maryland. You have Laurel again with a label Laurel.
Why, when, who would use that?
I don't know. I don't know why you would use it over the other, but I definitely see it a lot in legacy systems, like, for sure. And I see it less often than I do XML, but definitely people use it. And here I just want to make sure, like, if you encounter this serialization, you're not surprised, right?
How does that translate? I don't even understand how. Like, I understand how Turtle can translate back into RDF XML, and people do it all. We do it, but I don't even understand how N triple would translate back into Turtle or RDF XML.
Oh, well, like, see this, the HTTPS example Laurel. There's your hook, right? They're the same here, and so they're connected to the same thing. So are all the content that's hanging off of it, just like in Turtle. Like Laurel, off of that hangs the label, and then off of that hangs located in Maryland. And so if you're processing this and, like, translating it into Turtle, you would just kind of unify those. That's one step. And then something similar will go on in the XML, which is important to point this out too. All of these serializations can be translated into other serializations, with the exception of one I'm not going to talk about right now that I haven't discussed. But if you have something in XML, you can translate it into Turtle and back, and similarly for in triples and whatnot. Yeah, I didn't cover some of the ones that aren't exactly, but
why are they websites? This is a really stupid question. But, like, are there rules for how these are?
They don't have to be.
The webpage?
They don't have to be exactly. So it's mostly born out of early days when people were using identifiers on the web, and they were confusing locators with identifiers. And so HTTPS is like a way to locate information
Yeah.
on the web. It's not necessarily, it's not solely a way to like identify information or like stand for some information that's on the web. And so, but it was born out of that sort of time. And so it doesn't necessarily have to be like in this kind of locator strings form. It often is. Again, often because a lot of the stuff is on the web. So you can think of it as trying to locate information, but like conflate it in its early stages and often today as well with identifying, just being a unique identifier.
But so like I go to example.com/Laurel, what do I see there?
You
Is
should
it
see
literally
like
just a page that says Laurel? Is it a page that says Yanni? Like
it'll often have like additional information associated with it. I can,
Okay.
I'll pull up an example in a second, but like if you copy, say, the IRI or the URI, that's the International versus Universal Resource Identifier. If you copy that and put it in your browser for like BFO continuum parthood, you'll see like a snippet in HTML that will be representing like the IRI structure, and it's the annotations that hang off of it.
Okay.
Or you should, and if you don't, open an issue on the tracker because I got to fix that.
Yeah, like CCO, it's all resolvable. So like if you don't know what something means because you don't really know what, an information content entity is, it'll give you the definition, it'll give you alternate labels, it give you, maybe examples of usage, it give you
Right.
every single annotation.
Mhm. And honestly, I use this as this resolution in that format. If I see something come up in my working, I think something's gone wrong because I should never see that.
if you see
I could, like, if I go to that web page, if I'm like taken in a tool or something to that page, I'm like, the tool has done something wrong. I should never see that. What was I trying to do? That's actually how I would often debug stuff and like ontologies, like at least on the back end. I did this a lot at APL. Whenever I'd click on something, it took me to a web page with that information. I'd be like, bug, this is not where it's supposed to resolve for this tool.
So is what like when I'm operating with RDF, is whatever like I don't know, SQL, whatever like that I'm using to manipulate RDF, is it using any of the content on that page?
Absolutely. Well, it is using the triple structure that would be represented on that page.
Okay.
And it's Sparkle is the information extraction language. It's very similar to SQL, as we'll see later. But yes, yeah. In fact, you will write your queries in that, like reflecting that sort of structure, much like you would in SQL, like write queries reflecting the relational structure. Yes. Go for it. You're gonna Socrates me, aren't you? You're gonna be like, this is so simple. What is justice? Yeah, it's a series of tubes. So people speak of RDF and sometimes mean the vocabulary that implements the data model. And I'm actually going to show you the vocabulary in a second. I just want you to keep in mind that there are two ways of talking about it, and it's not uncommon for people to confuse them. And you can sometimes get into arguments about what you should be doing or can do with RDF that are actually questions about the limitations of a given vocabulary that you're using. With some caveats.
Not that you're using like RDF vocabulary into JSON vocabulary. That's not what you mean.
That's right. That's right.
You were talking about the formatting of the.
That's right. Of the file that you'll see on your computer. If I write the English sentence, the cat is on the mat in like, Garamond, and then I write it in Comic Sans. I'm sorry, that's the truth. And I write it in another font. I can translate between them. Semantics should be the same. If I use Comic Sans, it won't be, of course. But that was a bad example. But you see, if I go from Garamond to Times New Roman, that's closer to what's going on with the serialization stuff than like, yeah, none of the semantics should change. There is an exception to this, which is like an OWL format, which I'm not going to talk about right now. And also there's a, what is it called? Starts with a T, the tri format. There's another format that allows you to talk about like graphs directly and the triples, both the graphs and the triples. So you get quadruples. That's not translatable into these serializations. It's weird to even call it a serialization. Yeah. So let me move on to the vocabulary. Just some rules of RDF. Every fact must be expressed as a triple. Subject, predicates, and objects are names for entities represented as URIs. And then objects may be literal values, like numbers or strings, but subjects and predicates cannot be literal values. You can't have a string located in something. You can't have like John number to some other thing. Literals, they can only be in object positions. The vocabulary. So RDF in the data model sense is a simple data model, and it has a simple vocabulary that is associated in the abstract syntax, by the way. So it's not, there's a reason people get these things confused, the vocabulary and the abstract syntax, because that W3C documentation describes them both, though it's clear about which one's which. But this is parts of the simple vocabulary that they were introduced to describe that data model and have users like deploy it. So I'll walk through some pieces of this very interesting but yet simple vocabulary, like property. This is the class of properties, i.e. relationships among RDF resources. Remember, resources are like everything you can give a name to. So there's a property like structure here that you can leverage in the vocabulary, and it has things under it like type, which is an instance of property. And it's used to state that some resource is an instance of another resource. Like a table that you're putting your notes on is a type of table. Now, important, RDF does not distinguish classes from instances in its vocabulary. Strictly speaking, you can say you can say that a resource is an instance of another resource in the sense that, like, this table in front of you is an instance of that chair. There's nothing stopping you from saying such crazy things. That's fine. They didn't want to put like firm restrictions on what counted as a resource. They didn't draw a line between classes and instances. We'll get there, don't worry, but not here. In addition, statements. So its class of statements is, these are statements made about RDF triples, which is why you have these additional vocabulary elements, subject, predicates, and objects. These are used for what's called reification, where you want to talk about some triples. To give it an example, to reify in an old school RDF sense is to make a statement about a statement. For example, Sam might introduce a triple to an ontology of this sort. Butter potato is the type of potato. But let's say he wants to make sure this is because Gordon Ramsay says so. That's just to say he wants to represent that Ramsay believes that butter potato is a type of potato. How does it do it? Here's one way to do it. If you want to represent this kind of reification or this kind of like meta statement about triples, you can do it this way. Statement is about, or a statement here is the expansion of the content of that belief. The type statement, subject, butter, potato, predicate, type, object, potato. And then this statement here is what Ramsay believes. So Ramsay believes statement one, which has got this structure here. Yeah.
I have a question about RDF statement though.
Yeah.
How does it connect to? I always had a problem with understanding where, I guess maybe because I was using Protege, but of how it actually connects to the class that it is implying itself to.
I'll show you. It's all built into those brackets. Let me keep going. I'll show you. You'll see.
Cool.
Some other aspects of the vocabulary you'll run into. Bag. It's actually used as convention. If you see this, somebody screwed up. There's no semantics really around it. I just pointing that out. You see somebody using RDF bag, something they weren't thinking very carefully. List. Here's where I'm going to start unpacking some of those brackets. All right. Lists are approached the way like Prolog approaches lists. You have like a first element, the rest, and then an empty element. And it basically, you could probably see what I mean better with an illustration. So here's a list, A, B, C, D. How do you order this? Well, you have a first thing and then you have the rest. And then you have a first thing and you have a rest, and a first thing and then a rest, and the first thing and then the last thing, nothing. And that's basically how you get orderings out of these lists. And so they have representations for the first, last, or first, rest, and nothing. Does that make sense?
And you know, to group like what lists, like what do you make, I mean, demarcate, which is like where in the list you first and like last week, any like particular grouping.
You put first.
And then just like, okay.
Yeah, and it's read, it's understood that way, right? And then you have rest. Now, no, almost nobody's gonna spell this out. You're like the serializations don't even spell this stuff out. I will just put this bug in your ear. I did some very cool things once because I understood how lists worked in RDF. And I spelled out the list that was embedded in very complicated OWL semantics. And in doing so, I found a way to carve out a subset of the representation that, let's say, some of my colleagues thought was impossible to carve out. Can't tell you all the details because they told me I couldn't. But one day I will be able to tell you. Just know. Let me go. Example this: New England Patriots are a better football team than the Premier League football team Arsenal. Which is better than the Atlanta Braves. I did this on purpose because Carter was in class last time I was teaching this. These are not all football teams. The ordering involved can be represented in RDF as subject is a list, football rank, predicate implying ordering. First element is the Patriots. Rest is all that. First element of the second list is Arsenal, so it's recursive. Rest is Braves, etc. First element is the Brave or has the Braves, and the rest is nothing. And that's it. This is how you spell out the list. Again, you're not going to see this when you're looking at RDF, but if you know how it works, it can be very powerful. Yeah. And think if you want more insight into what I mean by very powerful, think about the way that lists can intersect with lists. And parts of lists can be targeted by other lists. Yes.
Is there any way to make rest into a variable to shorthand it?
Not here. But I mean, the way the variable works in a rendering that you'd see in RDF is it's going to have some brackets that are smuggling in like what you'll see in a second or something like existential quantifiers.
Be better to, could you make those specific labels be variables?
No, they're part of they're part of the vocabulary. So, you're not going to violate them. You can't like create or like well, you can't, so technically you can change the meaning of the RDF vocabulary. Don't, for reasons that I'll show you when we get to OWL, because there are flavors of OWL that will allow you to change the meaning of these terms. And but I will explain why you shouldn't do that. So technically you can actually change the meaning of this, but don't do it.
If you are making like if you're doing like a list
Mhm.
of like a whole class of all these and all the subclasses, is there a way to just group everything that's in like
There are no classes here.
What?
No classes.
If you are like for the instances of things like football
Mhm.
teams, and you wanted to list the first one, which would be the Patriots,
Mm-hmm.
and then if you say you had a list of like 20 others,
Mm-hmm.
is there a way to then just group them together without having to write all of them out specifically?
Yeah. You would do it. You would have list, and then you would just, in the syntax, depending on your serialization, you could just have Patriot, comma, Arsenal, comma, Brave.
Okay.
But then if you spelled it out, this is what it would mean.
Sans.
So obviously there's no like RDF second, but like how do you denote that something is second in the list? Like what would that look like? RDF
Check it out.
RDF.
Related to this bigger list, there's like, you can think of that as like nesting lists, right? And then the first, the top nest, you've got this element that comes at the beginning, And then within that, you have another list. There's number 2.
Oh,
And then within that, number 3.
nice.
And so if you're counting backwards, if you're thinking of this like a developer, you got nothing, 3, 2, 1, or
Nice.
more like 3, 2, 1, not 0.
Nice. Okay. Cool.
Yeah.
So what if there are two first? So what if there are four?
No. There are no 2 firsts.
So what if?
You're thinking of time, not lists.
No. What I'm saying is, so let's say Korean football team is better than both Japan and Thailand football team.
Mhm,
But Japan and Thailand football team are the same,
mhm.
right? Then how do you?
Wait, Japan and Thailand's football team are the same football team?
No, they are.
But they're like equals.
Ranked
Yeah.
equal in the sense that they're good there.
Yeah. Which is not true. Here's a way to do it. You make lists that have in one that you have the first thing that, like, whichever one you said was like greater than the others. And then you have it related to a list where the Japan's team comes first. And then you do it again related to a list where the Thailand team comes first. And so what you've had is you've essentially embedded that one comes before both of these two, and each of them come before itself or the other one. And so in both directions. Look at that.
And
Fun.
John, is this not used in OWL because it's not expressive enough?
This is not used in
Or is
OWL.
your example that you used showing how it's not expressive enough, considering that you used an American football team, a European actual?
No,
football-
I was
Okay.
mostly just because I was taking a piss out of Carter, but it's actually
I saw
too
the deeper
expressive.
meaning.
It's too expressive, as we'll see. This is largely not used because at this point we're dealing with a vocabulary that has like it lets you do basically whatever you want. Like it gives you very minimal guidance, and so all it's saying is like use triples, and so you can say some gnarly nonsense here. Before I show you some of that nonsense, though, a very important thing to point out. I'm showing you so far in these examples how RDF allows you to identify resources across the web with unique identifiers, but RDF also allows for the use of resources that don't have any specific identifier. This is useful because there are many cases in which one wants to represent, for example, that some X is related to a specific entity without being able to identify that entity. Which is to say, sometimes we want to represent existentially qualified information. Here's an example. Suppose you know that Barry plays the violin and you'd like to represent this with an object property, but you don't know which violin he plays. Question mark. Here's a way to start or to get some insight into how to represent that. Barry plays brackets, something of the type violin. What does this mean? Well, just what I said, but no, there's an implicit numerical ID being used here. This implicit ID allows other triples in the graph to refer to the same violin Barry plays, even though we don't know which one it is. It works like this. Barry plays underscore in the syntax colon something, blah, 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 that's related to a violin, blank node. This numerical ID is locally unique. It's important. It's locally unique, not globally unique like a URI. URI is always identifying the same thing. It's unique and it's globally so. These existentials are locally unique within a file. In fact, if you were to convert one serialization to another, the IDs change, which is a real problem. If you're working with different serializations and you have some of your blank node structures built into some architecture, because you can't trust that they'll always pick out the same thing in these embeddings. Here's some examples of what you see in different serializations with respect to blank nodes. RDF, XML over here, JSON, etc. You'll see the thing doing the work. In XML is this node, blank node ID. Over here in JSON, you see this ID structure. Over here in triples, you'll see the underscore syntax. In turtle, you'll see the brackets. You see brackets in turtle, there's a blank node. Now, this is going to be very important when we get into OWL, which is like the logical language, because OWL places restrictions on language like functional, symmetric, And the only way they work is with blank nodes. It's cool. It's scary. It's
Oh.
spooky. Because and blank nodes are needed in those sorts of cases, as we'll see, because you always have to convert everything. You always have to bottom out in triple structures. Sometimes you don't know the subject, especially if you're imposing like a logical restriction on something. You don't even need a subject.
Can you go back one?
Yeah.
Okay, so do I need to spell out the local identifier, or because in the turtle example,
Yeah.
you did not spell out the 001?
If you're working in turtle, you just use the brackets.
Okay.
If you're working
But
in triples,
you might need to.
yeah, so this is another reason why I prefer turtle. I mean, at this point though, I just run it all through GPT. I'm like, write it. but you get what I'm saying. I also don't want to read it.
Your violin 001, would you only use that in some type of closed world assumption where you're not moving it?
Well, I mean, it comes up all the time. Like, it depends on how you're using the files. I mean, you can't really, it's hard to get away from using blank nodes, period. And so instead of trying to avoid them, the strategy is make sure that you're either tracking them across serializations or none of what you're inputting or using in your systems relies on specific identifiers that are local to a file for blank nodes. You can rely on the IRIs or the URIs all day long, but just, be aware that if you put serialization, if you're putting in blank nodes or relying on blank nodes in this way, then once you do a serialization or come out with another version or something, you're going to break things.
But when you make an object property reflexive, you're really building a blank node in Protege. You just
That's
don't.
exactly right. That's exactly right. Which is again why I'm saying like the strategy isn't to avoid them because you're not going to be able to if you want to say anything interesting. It's more like management of them after the fact. There's not a way that I know of native to the vocabulary that will allow you to just track nodes across serializations. That's just not part of what the syntax allows. That is not to say that there aren't ways to manage this stuff. There certainly are ways. I'm just pointing this out because, I mean, you're likely to encounter this in the world because what I've just said to you about blank nodes is not very obvious to even a lot of practitioners.
John, a quick clarification. So are blank nodes known relationship to unknown instances?
Unknown in the sense that they don't have identifiers globally, but like locally you can refer to them like in the file, just like this is doing here. Like, so Barry is relating through plays to something, and that same thing is a type of violin. So you can refer to it at different places in the document. It's just that when you're thinking about this across serializations or versions of the document, those things, those like relata there will change. And so you can't relate them cross document or cross serialization to one another.
Is this something we're gonna need to know?
Abso-freaking-lutely. Why do you think I'm belaboring this?
So
Doing this for my health.
if we're using it for, say, object properties in what we're doing with transitivity and symmetric and asymmetric, you're saying that like when you change that from turtle to owl, they're going to become obscured? Or
so just what I was saying. So like as we'll get there, you'll see this. So the transitivity stuff, when you're applying object property like role constraints or role constraints to object properties, the way those role constraints work is by introducing blank nodes. And those blank nodes are like, you can think of them as placeholders that are needed to satisfy the triple structure format that RDF demands. And then like local to a file, you can refer back to those blank nodes. So like locally, they have like local identifiers that can be referenced in the document. But if you were to try to compare those specific identifiers to like reserializations of that document, which otherwise are the same, just in different fonts, right? Then you're not going to be able to do that pointing, that reference, or at least, I mean, you would be able to, because you could look at the file and be like, oh, that's what it means, but a computer can't. And you shouldn't trust your computer too, because as far as the computer is concerned, one file is gonna say 001 and the other file is gonna say like 00X. Because they're randomly generated. Definite descriptions versus names. I can describe Hesperus, I can describe phosphorus. It is sort of, if you're thinking of it in that, like philosophy of language terms, it is like this definite description versus unique identifier question, right? Like I can give you all the full definition or like a definite description of John Beverly right now in all my glory. It's gonna be long, it's gonna be beautiful, elegant, precise. Nevertheless, we could inhabit a recurring universe.
Is
Over
this
and
a
over again with
catch-all?
John. This is a little philosophical, but you could have like a recurring universe where this somebody with the exact same properties that's not identical to me repeats over and over again. Very analogous, one might say, to the serialization problem with globally or non-unique existential quantifiers.
Is this a catch-all for an area of RDF that is a limitation and a technological constraint of RDF?
Yeah, I think of it that
Is it being
way.
used as a catch-all? I really don't understand
Yeah.
how I can get a version of CCO in Turtle
Uh-huh.
and I can convert it to RDF XML, and how if I have something that's reflexive or asymmetric, how that translates, but why
Well, you're never
you said that you can't trust them, that they don't translate.
Well,
But-
you're never running like a reasoner across files, right? Unless you are. RDF is not the only tool we use. As I said, it's in many ways too expressive, and yet at the same time not expressive enough. At least the vocabulary is not, right? So folks have built vocabulary on top of the RDF. No, like this, an RDFS standard. So it's a scheme, it's a syntax and semantics for an intended extension of RDF. It is a vocabulary that is based on the RDF data model that extends the RDF vocabulary and provides semantics for connecting RDF resources. So as I said, we don't even have classes in RDF. You have them in RDFS. You will often see these two together. Even in the W3C documentation for RDF, there are references to RDFS class because it's so natural to introduce this information. So what is a class? We often say that X is a type of Y and intend Y to be a class. Strictly speaking, as I was saying in RDF, there is no such thing as class. RDFS class introduces a syntax needed for such an assertion. It's exactly what you think. Like repeatable things are classes, instances are not. Also, we want to relate classes to other classes. The subclass facilitates this, and it's represented as we often use, and is a hierarchy. For example, BFO object is a subclass of BFO material entity. Binary relations, more semantics, love it. For binary relations, the domain of R is whatever can occupy X, or RXY. The domain of R is whatever can occupy X, and the range is whatever can occupy Y. That's what we mean by domain and range here. John loves candy, all candy. I'm a human. This loves relation, as far as I'm concerned, only relates humans, i.e. me, to candies, i.e. all of them. Domain and range. Suppose we want to define a binary relation has leaf. Plausibly, the domain will be plant and the range will be leaf. Subproperty relationships too. I was just talking about relations. Now, again, confusingly, they call relations properties. Silly. Nevertheless, we'll deal with it, much like we do with most things in our political environment. Much like we often find a need to describe is a relationships between classes, so too we need to describe is a relationships between relations, such as X devours Y being a subproperty of X eats Y. There's also RDFS resource. Recall in RDF, we were talking about resources, but we didn't say any vocabulary about resource. Crazy, right? Yeah. This is the class of all the things, is an instance of RDFS resource. Any class is a subclass, for example, of RDFS resource. RDFS resource is all the things. Now we have a way to pick out all the things.
I just want to make sure that I understand what a property is in this case, because we're not using it the way that philosophers will.
No,
Like,
it's a
and
relation.
We're not, it is referring to a relation. Okay,
Yep.
so it's the, good.
Computer programmers. In addition, data types are within scope. A data type is a subclass of RDFS literal, which will come in a second, and is the class of all data types such as integer or decimal. There's a well worked out standardization around data types that you can see here. There are logical relationships among them. They're standardized domains. Integers include, for example, all of the integers. Decimals include decimal stuff. Incidentally, speaking of a decimal, just want to give you an anecdote. You guys know who Richard Feynman is? He has a funny, wonderful quote where he in one of his lectures on physics, he's expanding pi. He's like, pi 3.141592, and he goes on and he doesn't string it out. He goes, it goes on like, and at some point you get to 777. Apparently there's a string of sevens in pi. It's like 13 sevens in a row. And so he'll say 7 13 times and then he'll go, and so on, and then moves on in the lecture. It's fantastic. Just brilliant. Anyway, decimals. What he just said was in there. Covers them all. A literal relates resources to strings, such as data typey things, which can be plain or typed. And typed literals are strings with an associated data type tag. Plain literals are strings without such things. For example, Mexico-Arizona border has longitude and value, string, XSD decimal. Also has a nickname, the border, with an ampersand meaning English. It's an English language tag, which is not a data type, but it is a tag you can apply to strings. It's still untyped. Also, down here, you've got 2, the number 2, as a string, not a data type. It will be interpreted differently if you put a data type like integer on it than it will be if you just put quote 2 quote. One of those has some logic associated with it. One of those has background checks, which I'll show you in a second. Yeah, Jay?
When you put en or any language, is the default XSD string?
Yeah, as far as I know, as far as I've used, that's right. But it works like this, right? Like whether it's with the language tag or the XSD data types. So in this case, it should illustrate both to some extent. So XSD data type semantics are already integrated into RDF. S, and they allow for logical comparisons, equality, and calculations. They're composed of 2 pieces: of value space, which are the values the data type can represent, like integers has value space, all integers, and lexical space, which are the strings representing valid values for a data type. For example, integer has a lexical space that includes strings such as 1 and -4. This is important because some values have multiple lexical representations. The lexical representation is not always like exactly what you would see in a value space. So integers can be written in different ways.
Can you go back one slide? One more, sorry. I just wanted to. Plain. Okay, what is plain? Is that just means it's untyped?
Plain vanilla,
Untyped.
plain and typed. Value and lexical space. You get no real logic from just the string, except the following: minimal logic. If a string is exactly the same as another string, it is processed as such. If there's any deviation, it is not.
And type.
For example, yeah, go ahead.
Type in this case refers to a data type.
Yeah,
not
data type.
The earlier.
Yeah. So when comparisons are conducted, for example, by our reasoners, XSD data type definitions are used to ensure, for example, integer comparisons are conducted numerically. So integer is less than this integer, 3 is less than 30. That is conducted according to integer characterizations of data type. Strings are compared lexically. Friend is identical to friend, but not friend with a capital letter. That is the minimal logic for strings. Dates are ordered chronologically. So data type, like the date timestamps have this logic built into them and you can rely on. So why am I pointing this out? Well, why would you represent this in your ontology if it's already built into the background logic? Spoiler, you wouldn't. Just leverage the logic. Dates are ordered chronologically. For example, 12/2/2023, as we can all agree, is before 12/2/2024. Label. Annotation property allows you to provide human readable names for resources, so you don't need to look at those ugly URIs all the time. Like this, check it out. There's BFO, in all its glory. When you see in Protege as a label, you don't see that ugly URI that's associated with it. You can see it if you look up here above annotations and usage. You see HTTP, Perl, OBO library, OBO, BFO, 00, something 2. Like that's what the computer cares about. This annotation, this label hangs off of it. Also, so comment is also an annotation property that allows you to create comments on resources, maybe suggesting updates or changes or something or disagreements. Maybe you don't want to put this in your like main branch, but maybe develop or something just to keep people like, hey, check this out, keep looking at it. As you can see, here's a comment that I put on, continuing, hey, it's me, I'm a comment, help, it's dark, I haven't eaten for days, I've lost count, the rats will be back soon, I can feel them watching, waiting for me to sleep, waiting for the world to fall away like tears in rain. You probably won't want to put this on your main branch, but maybe develop. Anyway, defined by is an annotation property indicating the primary location of a resource's or like definition, such as this BFO OWL file, which is where you can find the definition for entity as it's represented here in the cell line ontology, which imports BFO as its top-level architecture, because BFO is the home of entity. It's where they all live. It's all the stuffs.
So RDFS is the meta language for RDF, unless you're going to start doing reification. Like that's kind of the only way I can see that you would.
No.
No.
RDFS is an extension of RDF that introduces more vocabulary, so you can do more things. If you're thinking about it in a logical sense, it is RDF is a very weak, high-level abstract language where you can't even formally distinguish between classes and instances. And here you can do that and much more. You can restrict domains and ranges of relata. You can introduce properties and subproperties or subproperties of properties, etc., which is a way to like restrict the usage of RDF into a specific, very intuitive, in a very specific, very intuitive manner. It rules out, putting it another way, it rules out other uses. For example, like treating or saying that a table is an instance of John, because it imposes semantics that kind of excludes those sorts of cases. Of course, you could still say that. It's just now we have the vocabulary to say exactly why you're wrong. Yeah.
Are there blank notes so in RDF?
There are blank notes everywhere.
No, in RDFS, are there blank notes for classes?
Not in the vocabulary I just showed you. Yeah, they come up because they inherit them from RDF. Blank notes come up even more prominently in OWL, which is where we're going next. See, it's like you're a plant and you have a leaf. OWL, web ontology language, our bread and butter. It's got ontology right in the name. W3C standard. It's a family of vocabularies that extend RDF and RDFS, and they provide semantics for constructing logical relationships among resources. This is where the logic comes in. We will focus on OWL 2. It has a clear connection to description logic. It's well understood, well defined, great documentation. The vocabulary includes terms like that you've seen already from a previous discussion, that big T, the upside down T, etc., but also complex combinations of description logic syntax such as disjointness. And this is what you would see. Well, this is what you would see in an OWL file written in Turtle. In fact, this is the OWL file in Turtle. And as I was saying, those symbols, they're represented in the language here. That bottom, remember, if you recall from the description logic syntax and the semantics, it meant nothing. It was the class of things that was nothing, or not everything. You see that represented here just straightforwardly as nothing. And what is it? It's the empty class. You got a comment there explaining it. This defined in what? This W3 2002-07.org blah, blah, blah file, which is actually the file that we're looking at here. The label is nothing, and it's a subclass of thing. Because even nothing is a subclass of thing. That's the logic. And that is true in description logic as well. It also includes these other symbols that you saw from description logic, right? Like union of. What is that? It's a property that determines the collection of classes or data ranges that build a union. You're combining things together. Disjointness. Disjoint, there are two versions of this actually now. You have disjoint union, you have disjoint with. Starting with the bottom, disjoint with is just a property that determines the two classes are disjoint. Straightforward. They have nothing in common. If class A is disjoint from class B, there are no instances they share. Disjoint union of is a property that determines a given class is equivalent to the disjoint union of a collection of other classes, which is a terrible definition because they just put disjoint union. What's that? But really, it's just this disjoint union. You take disjoint A, disjoint B, and you introduce a new thing that is the union of both of them. Let me highlight this. This is a point that, again, in my experience, often generates a lot of confusion. The logic works like this. When you have disjoint union of A disjoint union of B, you're talking about a class disjoint union of, a class disjoint union of a list of other classes. So A disjoint union of, say, B and C. B and C are disjoint. A is the union of those disjoint classes. That at no point entails that there is any one thing that is both B and C. Quite the contrary. It entails anything that's B is not C. Anything that's C is not B. It can be A and not be both of those, because A is the union. Yeah.
Is this like entity equal to one another?
Yes, very much so. If you're thinking of entity as the disjoint union of continuance and occurrence, saying that there is a class entity that unions them together is not to say that there is anything that is both a continuant and an occurrent, because those are disjoint. I'm emphasizing this, and I hope you get the logic down. I'm emphasizing it because I have probably had more conversations about this point and as far as the logic is concerned, more regularly about this point than any other conversation I have about OWL. I have a canned text message that I send to people that describes this because I've had to text people so many times how this works. So, but I think sometimes it just takes a minute to think about it and understand it. So I'm trying my best to explain it to you in a very clear, careful way. But if you're not getting it, just take the heuristics that I'm giving you down, like A disjoint with B and C, or an entity disjoint with continuant and occurrent, means that anything that falls with an entity is either a continuant or an occurrent. Nothing is both. Okay? Take that example, yeah.
That is not in A or C is not in A, right?
You have to say that without all those knots.
Okay, so it means that there are nothing that is outside of B and C but is in A, right?
Not quite, unless A is everything. Do you mean A? If A is everything, but you could carve up like a subset of all the things.
That's this.
Yeah, that's right.
So B and C are disjointed, they're neither entity in either class is in the other. A is the set of each class just together.
Yep,
And anything in A is either one or the other.
that's right.
Okay.
Disjoint union.
So this is maybe a dumb question, but is the disjoint union of two sets retaining the structure of those two sets? So like I can say there's XYZ in B and 1, 2, 3 in C. Is A equal to the set B and C, or is it equal to
Or
X
union C.
or B comma C, or is it equal to A, B, or XYZ comma, 1, 2, 3.
Yeah, it's like the collection. So
Okay.
the union is all of those things, right?
Yeah,
It's
yeah.
all the
So it's-
instances.
It's
Mhm.
just taking out the
That's right.
content.
That's right. That's right.
Okay, good.
Just like entity, if you're just looking at entity without thinking about continuance and occurrence, and you just have a big grab bag,
Yeah.
you're gonna have a bunch of continuance and occurrence.
It doesn't import the structure of those.
Not across them. Like occurrence in the case that I just described are still gonna have all the structure that occurrence have. They carry them with them because they're occurrence, right? But there's no continuant occurrent, right? There's nothing that covers both. Does that make sense? Yes.
Is this how you decide when something isn't an equal subclass of something and something is its own entirely new entity?
This certainly goes into it. Like if you can,
Like, do you use this in the argument of what's a role and what's a disposition? Is that like part of like the decision between like deciding that role and disposition are separate realizable entities?
no, this would be like a way of representing the decision. But the decision was made at like a kind of more argumentation based level. So higher than the semantics and higher than how you would represent it. It's more like there are things that are realizables that are grounded in material bases, and there are things that aren't. They're more like contextual based, and so that was kind of the real dividing line between like roles and dispositions. But that's all like reflection on usage of these terms and things nearby, and also like arguments for one way rather than the other, and philosophical considerations that informed drawing the distinction in the first place. But then that is like, once you do that work, then you want to implement it in a way the machine can read. And so then you might enter into disjoint stuff, like talking about disjointness as a way. Now, this is a great point that Jay is raising, because here's another thing to keep in mind. Sometimes you will encounter ontology engineers who, when you press on some distinction that's being drawn, they will say, well, it's in the logic. And as if that's an argument. That is not an argument. Just because the argument is supposed to justify the logic.
Yeah.
The logic doesn't justify the argument. So you're not going to convince me that two things are disjoint by saying I can represent them as disjoint. Because I'm going to be like, why? I was asking you why. I can represent all sorts of things. I can represent them as not disjoint. What's your point? So this is a good point, though. You will see this often be on guard. Representation in OWL doesn't settle disputes.
I guess my question is, the question is like, when we're subclassing things, right? And we're trying to figure out like, well, is this the subclass of this, or is this its own new thing?
Yeah.
Right. And I think that we've had these arguments that we've worked through with information content entities. Like, okay, like I think there should be a lot of different types of information content entities, but like if I'm looking at like continuant fiat boundary, there's an argument to be made between a zero-dimensional continuant fiat boundary, a one-dimensional, and a two-dimensional, that you can say they're all disjoint with each other. I mean, that is something that you would have in your logic, I would think.
Yeah.
Is that a defining factor for when you're building to say, well, these are different? I'm having a hard time thinking on top of my head of a material entity that I would use this for, but I just wondering if that's sort of part of the argument for building really sound ontologies, is to use just joint with to decide if things are really intrinsically different.
Yeah. So here's a way to see the picture. I'm sorry, I'm sprinkling paper. I'm starving, but let me put that inside. So here's a way to see the value. So again, like we'll keep the distinction between the arguments supporting the logic and the logic itself. So if you're thinking about continuous fiat boundaries, let's say for the sake of argument that you want to say that the disjoint union of continuous fiat boundaries is the 0, 1, and 2-dimensional continuous fiat boundary classes. So what you're saying in that case is there's no one thing that is all three. And there are no other boundaries. Like there are no other types of continuant fiat boundaries. It's exhausted entirely by the class continuant fiat boundary. So that itself, that representation wouldn't inform the argumentation for it, but the argumentation for it might inform that logical representation. If you don't believe me, go get on GitHub where we're talking about on the BFO repo continuant fiat boundaries. And let's just say somebody on there not too long ago was like, but look, it's in the logic. And I was like, bad move. So this
Okay.
comes up all the time. Like, okay, but then back to but back to the.
I mean, those statements are true I made because one
Sure,
dimensional
yeah.
continuant fiat boundaries are disjoint with 0 and 2-dimensional, but it's not the full case for the premise that they should exist independent of each other.
That's exactly right. And here's some contrast, right? You may think that there are such things that are continuant fiat boundaries that are 0 and say 1-dimensional. And if you are saying the disjoint union of continuant fiat boundaries is just exhausted by these classes, you can't say that. You can't say that there's a 0-dimensional plus 1-dimensional continuant fiat boundary or 1-dimensional plus 2-dimensional continuant fiat boundary, because what you've said is all the continuant boundaries are of these 3 classes and nothing else, because they're disjoint union. It's all of these. And so you've closed off the world. This is important.
Unless you believe the earth is flat.
Unless you believe the earth is flat. You believe a lot of other things. But disjointness, asserting disjointness, that brings in a lot of logical power. So if you could say that these things are not those things, in fact, are not any of those other things, you actually provided yourself and reasoners that you'll be using information to allow them to like exclude patterns that are bad or exclude patterns you're not interested in. Logic works fundamentally by excluding things. Like if you're asserting an axiom is true, you've just asserted that a bunch of other things aren't. Because as far as like a reasoner would be concerned, unless you do that assertion, everything's up for grabs, right? When you're asserting, you're ruling out alternatives and you're saying these are the ones I'm interested in. Disjointness does that explicitly. These things are not like that. If you didn't assert disjointness between continuant and occurrent, as far as a reasoner is concerned, there is such a thing that is both a continuant and an occurrent. And if it generates a model, like an abstract logical model, there will be such things. One of the reasons why we assert that there aren't such things is because there aren't such things. Like we argue, right? And then we say when we're building models using reasoners or logic, we don't even want to think about those sorts of things. Now that doesn't answer the question about like when to make the decision.
But they're important and they're really powerful, right? I mean, like like for example, say in the future we find out in science that actually these aren't disjoint, right? Continuance and occurrences aren't. Then we would have to deprecate both continuant and occurrent and create new attendance and concurrence, because in this situation, the disjoint width is as powerful as the primary elucidation or definition of the class.
That's exactly right. And one day, I would be so surprised if some scientist identifies that there are continuant occurrence. I cannot even imagine. But that is also the case for the rest of BFO. Yeah, GC.
Exactly what to say that like, oh, but like continuous and occurrent, those are classes that are analytic, not like synthetic, like.
I think this is part of what Jay is pointing to. They're analytic in the sense that we're defining them this way. And but what he's pointing to is if we have evidence that there are such things that are both continuous and occurrence, we are trying to respect science, right? If it did happen, because they're analytic, we have to jettison them. The same way researchers back in the day analytically defined phlogiston and had to get rid of that theory because there is no such thing. You know what I mean?
Yeah, it's one of our major principles inside of, well, in OBO, it's a principle, and that, you know, like from when Pluto went from a planet to not a planet to a planet, not to a planet, you know, like change that.
That's right.
But that's in the sense of Pluto, it changed because the concept of that class planet has changed, not because any empirical. But that's what
John, we can't hear her. Can she speak up?
Yeah.
We literally can't hear anything she ever says.
GC was saying that she's suggesting the concept of planet change. Right?
Yeah. So what
Can you please speak up? I just want to make sure they can hear.
So what I'm saying is that in case of Pluto,
Mhm.
of course, over the time, the scientist has accrued a lot of like empirical information about Pluto. but it has really nothing to do with how we define those kind, like the planet kind. The planet kind concept has evolved. I mean, I get that because it is based on the empirical findings. But what I'm saying is that occurrence and continuance are even more analytical. And isn't it, aren't they more analytical?
Maybe we'll put this, just a couple of things. So one on Pluto, what happens is the planet was underspecified. And so what happened is that researchers got together and agreed that there was some additional aspects of planet that they should have included, namely like, is this celestial body, does it have control over its like orbit? And Pluto doesn't. All the other planets do, and that is like a distinguishing differentia, which they've used. And so they've like refined the notion of planet to that it ultimately excludes Pluto, like born out of these conversations. So that's one thing. And then two, I think maybe what you're trying to point to is that what I was jokingly saying, like, how would you test this? What researcher is going to come along and be like, that thing's a continuing occurrent? Told you. Like, I have no idea how to test it. It's because it's so high level, right? Like, and that's part of the reason we stick in BFO at this really high level. It's supposed to be insulated from it's basically it's metaphysics, right? Like it's a frame, it's a way of organizing things at a high level for science, not exactly in science, even though science uses it. But you're not really testing this stuff. So I think that might be the I mean, it helps me sleep at night because I'm like, good, I don't have to like revise BFO. CCO on the other hand.
But if the test is intrinsic upon class, then it makes sense that like if Pluto is not a type of class of planet, that you can't test it against type of class of planet because type of class of planet now has changed. It's sort of like that's
Yeah.
really important if you look at like just material entities within industry. You
Mhm.
want to be testing things against its own class, and if you decide that the class changes or you've expanded it and now you have to move this instance to something else, then you would not want to test it with a bunch of other things. It wouldn't be fair to the test.
It really wouldn't. You know, it's funny. So you guys know this applied ontology case studies special issue that came out in the journal Applied Ontology. It had like Dolce case studies, it had BFO case studies. There were like 8 case studies about change over time. So we wrote papers that represent different changes over time. The last case was about Pluto becoming or like not being a planet anymore. And we were the only team that represented it. But basically, the way they didn't include it because we were the only team that represented the case. But basically, the way I thought to represent it was by comparing different ontology files, not exactly the classes as we would normally do within the same file, because there was a deprecation that went on. And so it was like kind of more configuration management at a meta level than actually ontology representation. I think that's another reason why they didn't like it, because we're supposed to be representing things in the ontology, not about the ontology. But I feel like that's the way you would handle that case. Things get deprecated, and we still might want to make assertions or claims or have meta information about cross ontology occurrences. Yeah.
I mean, so that, like, the Pluto case is like kind of a classic case of nomological construction, or response dependent.
Have I not given you enough jargon in this class, and then you're just bringing up nomenological
Man.
construction?
I'm saying that there's a cool philosophy thing that it turns out ontology can do. Congratulations, guys.
You said cool. I'll be the judge of that.
Is that also why
what?
from an IRI situation, you should never use a human readable IRI in anything that could possibly ever be deprecated? Like for here, disjoint union of could never be deprecated because it's right, but something like Pluto can. So the problem is if you give Pluto a /Pluto IRI, and then you have to deprecate it because you have to make a new Pluto, you're
Yeah.
kind of screwed.
I mean, honestly, I wouldn't even want to use human readable IRS here, because what is this? Everybody speak English? Like, come on, man. Like, there are other languages.
Well, I agree with you. I'm in the non-human readable camp.
Yeah, identity. So, Jisoo, you had mentioned, if I recall, what if you're relating one thing to itself? There is an owl predicate for that, same as, and it links instances of things to instances of things. You can read it as identity. It's the identity symbol, basically. But importantly, keep this in mind, it relates instances of things to instances of things. You're never going to relate. In fact, as I'll show you in a minute, you're never going to relate instances to classes in this vocabulary. Also, there's the sum values of, remember from description logic, This is the property that determines the class as an existential property restriction refers to, not very helpful, but the way you spell this out is for all things, remember that implicit universal, for all things X, there's some Y such that X relates Y and Y is a C. You also have role constraints like functional, inverse functional, transitivity, symmetry. For example, functional properties, very helpfully described as the class of functional properties. Inverse functional, similarly helpful description. What does functionality mean? Functionality just means if X is related to Y and X is related to Z, then Y and Z are the same thing. Inverse functional is the other direction. If X is related to Y and Z is related to Y, then Z and X are the same thing. So, do. Functional, collapse, inverse functional, collapse.
Can you say that?
I guess. Very functional. If X is related to Y and X is related to Z, then Y and Z are the same thing.
Yeah,
In,
it's a mathematical function.
That's right. In inverse functional is if X is related to Y and Z is related to Y, then X and Z are the same thing. So this is why I was doing this chomping thing. Functional, two things collapse to one thing. Other direction. Inverse functional, two things collapse to one. Also, we have in OWL 2, instance declarations and negative property assertions. Just a second. So instance declarations, we allow for naming specific instances of things. OWL named individuals, the class of individuals, the instances, this table here, me, this watch. That's how we pick them out. We label them this way. OWL negative property assertions. This is very powerful. As a matter of fact, this asserts when things are not related through a given property to one another. So if I want to say that John loves Arsenal, this is a soccer team. Darn, if Carter was here. John loves, if you want to say John does not love this team, and I don't, honestly. I'm mostly because I just don't know about anything about him and I feel like I'd have to care, but I don't. It's loving entails caring. Now, I could say that loves relation, the way I would represent it is as a John loves blah, 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 and loves negative property association with it. For this relationship, the specific instances do not hold together under this relation, which is another way of saying John doesn't love Arsenal. It's an instance. Let me highlight something for you. Just as kind of like a limitation of the expressivity here as a segue into the expansion or into the next section. You might want to say that, let's say you're given an image and you need to like say in this image what you're seeing. That's a truck, right? That's a caravan. That's a tank. Let's say you don't exactly know what the thing is. In fact, it's really hard for you to figure it out, but you can say, you do want to say what it's not. You want to say it's not a cat, for instance, right? You can't exactly say that here because you're only able to, in these vocabularies, to relate instances of things to instances of things. That's how OWL works. You can't relate an instance to a class. And if you wanted to say not a cat, you don't mean a specific cat. You mean all of the cats, which is like saying, I don't want this, there's nothing here that's relating to all the cats. Most you can say, OWL negative property assertion here so far is that this image does not represent Garfield or my cat Otis. Specific cats, right? There's a gap there. Now, why am I bringing this up? So OWL 2, we've been focusing on OWL 2. So a very specific semantics that lines up with description logic. But OWL 2 itself comes in different flavors. What we've actually been describing is the direct semantics, the one that lines up with the description logic. There's also a full semantics. The full semantics allows you to point to classes that way. The OWL 2, though, was designed for reasoning support. and hence all this focus on logical connections. But combining RDFS and OWL2 vocabularies without any restrictions results in a language that's too expressive for reasoning. OWL2 full uses all of the OWL2 vocabulary and allows arbitrary combinations of this vocabulary with RDF and RDFS. This is what I was mentioning earlier when I was like, you can change RDF and RDFS in some flavors. This undermines efficient reasoning in part because arbitrary combinations of OWL2 and RDF allow one to change the meaning of the predefined words or vocabulary of RDF and OWL2. For example, in OWL2, you can say, or I'm sorry, in OWL2 full, you can say, impose a cardinality constraint on the class of all classes, thereby limiting the number of classes that can be represented in an ontology. You can say no more than 3, and you can put that directly on the class in RDF, right? That's changing the meaning of the RDF vocabulary. Similarly, you can relate any instance of a class directly to another class. You can't do that in RDF or RDFS or OWL2 with the direct semantics because you can only relate instances of things to instances. You can't directly relate classes to classes. The RDFS subclass of relation, for instance, is a relation that links instances of things to instances of things, not classes to classes. Yeah, that's the interpretation. Yeah. We've, again, been focusing on the direct semantics. The direct semantics is a restriction of the OWL2 vocabulary by mapping it directly to a decidable description logic. It lines up with a decidable description logic. Notable consequences include OWL2 vocabulary terms cannot be applied to each other. You can't apply a part of the OWL2 vocabulary to other parts of the vocabulary. They're off limits for that kind of relation. All OWL2 classes are instances of OWL class rather than RDFS class, which is the bigger class. It is a restriction. Note, if you are in the future writing queries or trying to extract information from ontologies, from large ontologies, maybe that have been put together from various individuals, you will undoubtedly come across people using both OWL class and RDFS class, sometimes in the same ontology. I will show you how to keep on guard and write your queries so that they can cover both, but just an FYI, this generates a lot of confusion. And sometimes you can write queries that miss a lot of things because you're not keeping in mind that there are different classes, one for RDFS and one for OWL.
We had to do this.
Yep.
It was terrible.
It's
Yeah.
terrible. Yeah. In addition, OWL2 properties are either OWL object properties or OWL data properties, but not both. You're not going to get both. They're object properties that relate instances to instances, or data properties that relate instances to literal or like strings or data types. OWL2 resources cannot simultaneously be class, property, and instance. Not logically. You can label them whatever you want. You can say there's a class cat. You can say there's an instance cat. There is no connection between them. You can say that class cat has one instance, which is a cat. You could say that. That typing is the only relationship among them. OWL2 can be used by standard reasoning, one finds in, say, Protege, but OWL2 full cannot. So direct semantics is implementable, full is not. There is no reasoning support for the full semantics. Yeah.
Can you go back?
Yeah.
So the OWL2 resources cannot simultaneously be class, property, and instance. Is that it cannot be L3 or it cannot be any pair?
Any pair.
Okay. I mean, that makes sense.
Yeah. Important takeaways. Simple RDF will often need to be extended to be useful. Extended RDF will need to be restricted to be useful. Any legal OWL2 description or direct semantics, that's the DL, file is a legal RDF file. It's not the case that any legal OWL2 DL is a legal RDF file, again, because sometimes if you're thinking about the full case, you can change the RDF vocabulary by putting restrictions on it, which is not RDF anymore, it's something else. What description logic? I said OWL2, the direct semantics, the one we're interested in. What description logic? It's SROIQ. This will be fun. S is just an abbreviation for ALC. Remember ALC we talked about last time? We did. We talked about ALC last time.
How is S?
I have no idea. Computer science. No offense, guys, but like it, I actually have no idea why. It's yeah, but you know, it's better than alkeroic. Right? So S, ALC, remember this? Here's the syntax, you got the union stuff, negations, etc. You got the interpretations, just some math. I won't go through it again, but basically you got concepts and classes and relations, etc. I'm going to skip R for a second because it's going to be interesting. But just to remind you again, nominals. So O was nominal. Why is O nominal? Not sure. I think it's because ontology. I don't know. But remember, nominals, this is how we introduce names. And remember, you do that little set theory trick where you introduce singletons so you can union them together. We have inverses in this language as well. That's what the I is for. So loves and loved by, continuant part of, has continuant part, stuff like that. And then qualified cardinalities. There's the Q, which allows you to put, relate to no more than NCs, relate to no fewer than NCs. Like this is part of the expressivity. You'll see it in OWL because it's a direct reflection of this description logic. Now the fun one, the one I skipped over, R, role axiom extensions. You'll see this in Protege, but in OWL as well. This is render in Protege. You see a little box like this in Protege that'll have like functional, inverse functional, transitive, symmetric, asymmetric, reflexive, irreflexive. You can just click these little buttons on object properties and it will impose restrictions of this sort. Inclusion. Now, that was not one you saw there, but I'll let you know what it means. Allowing role inclusion axioms facilitates chaining of roles, such as if X owns Y and Y is part of Z, then X owns Z. That doesn't seem true. But anyway, it's an example. So role inclusion axioms have this form. If you're thinking about like the mathy stuff, it's right there. I'm not even gonna try to read it, but not just any role chains are allowed. There are too many. You see why we first distinguish simple and non-simple role chains. Remember, they have to have this form. Any role inclusion axiom where n is 1, we'll call simple. And for any role inclusion axiom such that every role in that axiom with n greater than 1, we'll call a non-simple. So the multiple of the R's. Every role in a simple role inclusion where one is a sub role of the other, for instance, with a non-simple S is itself non-simple. Every R inverse where R is non-simple is itself non-simple. And no other role is non-simple. Let me explain with an example. Which of the following are simple and which are not? Think of them together, all together. Don't worry, I'm not going to make you think too hard about it. It's getting late. The sun's going down. According to one, if there's a role chain consisting of more than one occurrence of a given role, that role is non-simple. Non-simple. What do we infer from this? Ancestor of is non-simple. We can conclude then that. We can, moreover, according to 3, and the fact that ancestor of is non-simple, it follows that ancestor of inverse is non-simple. And by 2, because ancestor of inverse is non-simple, so too is descendant of inverse. The rest, but lastly, by 4, all the other ones are simple. So mother of, parent of, etc. Now, to maintain decidability, we have to restrict non-simple role inclusion axioms. So all the simple ones are fine, but the non-simple ones, we're not just ruling them out entirely. We can allow for them, but we have to restrict them to those that have the property of being regular. Without going into too much detail, this just means if you're going to have role inclusion axiom or chains, then any combination of them and their inverses have to exhibit a strict partial order, like a little tree structure. I'm not going to go into the details. You can ask me later. It gets kind of technical and hairy, but that's the idea. And don't worry, you will also explore some of this in your project.
Now I have a question about just
Yeah.
role axiom extensions.
Uh-huh.
So they're using blank node to be described within the language, but since they're role axiom extensions in OWL2,
Mhm.
therefore, anytime that I go from I have an OWL2 file in Turtle to an OWL2 file in RDFXML, those role axiom extensions are expressed in the file. So therefore, they're not going to be blank nodes that are unknown. They're always going to be known. Because you already have the legend, basically, because you're using OWL2.
If you're using the local file without reserializing or without changing it, but it's really about the processing, right? So like you take the file, like if you're reading the turtle file, just the one I was showing you on the screen. If you take it and you put it in your system, you put it in Protege. What's going to go on is as it's processing it, or as Protege is doing the processing, it's assigning blank nodes to your file. And if you're continuing to work locally on that file, you continue to work with it and like play with it and whatnot, those nodes aren't going to change. Now, when I do it on mine, it's going to have different identifiers. And if we were interested in like doing a cross-file comparison that was focused on the nodes, those blank nodes, the blank nodes, not the other ones. The unique identifiers are fine, but if we're focused for some reason on connecting or looking across our files, those blank nodes, where we're going to get mismatches. Now, most of the tooling doesn't do that, so you don't often see it. But if you are like trying to say integrate different or changes from different groups, like who are all working on a similar file and they're making updates, depending on how your workflow goes or your QC stuff goes, you may or may not see in a diff a bunch of changes to blank nodes because fundamentally that's happened in these different iterations, or they're being pushed up in with different like blank node structures from different files. Now, again, like it's easy to get around those sorts of cases because what you do is you use all the graph structure around the blank nodes to indicate like these are actually the same things. And so they resolve in the back end. Most people don't even know it, right? But
what would know it? Like if I'm building, if you send me a bunch of turtle files and I'm like, well, I have to convert them RDF-XML because that's what our principles document says when we publish, and I publish those, right? And then you go out and you build robot X and I build robot Y and they're supposed to dance the cha-cha together. And
yeah.
Are they not going to be able to? I mean,
no, they depending on how, I mean, hopefully, yeah, but like it also will depend on how you build your architecture. So if we're building them like separately and we are connecting but like fundamentally the way we've approached connecting these things has to do with the blank nodes and like whether there's an identity between blank nodes across our files, then we're going to get into a problem. But even in that case, there's a lot of logical structure around the blank nodes that we can leverage to get in consonance and dance together. So we don't often need to get to that fine grained level. Now, there are cases, especially if you're working in like workflows of the sort I was describing or doing QC stuff, where there are those like connections and you want to make connections across the like really, really deep down blank node level. But again, for most of the time, most part, we don't run into those problems. Protege 2, by the way, like it like leverages the logical structure around blank nodes to resolve or like to kind of consolidate files. So you often don't see this. And that's the same sort of thing that would go together if we were like trying to combine our files. Like there would be some resolution, and the blank nodes would have all this other structure around them that would help the processing sort out what was supposed to be connecting and what's not.
but if you emailed me and Matilda the same exact turtle file, and we opened them up in our own instances of Protege, and you said, okay, do this, then do this, then do this, and we saved, and we sent them back to you. You're telling me that they would have different diffs?
Different blank node structure. If your diff, yeah, you'd be able to see this if your diff shows the blank node structure. And again, you don't often see this because most of the syntax is smuggle in the blank nodes. But if you're like, say, look at n triples or something, you're going to get different nodes.
Wild.
Yeah.
That's wild.
So
Okay.
are the files different though now?
So they
Are
are,
they intrinsically different? So I've converted now and we
Yeah,
no
yeah.
longer are operating off the same sheet of music,
So
right?
what they call it, what they say is there's a structural similarity and then there's like semantic similarity. This is a distinction that comes up in the documentation. And so they are structurally the same. And most of the reasoning and stuff you need to use is at the structural level. But like the real fine grain, like actual deep semantics, they are different because they're pointing to different nodes. But like, again, structurally, this is what I mean by like all the logic built around it is usually all you need, and that's the kind of the place the tooling focuses on. But there's this that level is the same across these documents. Yeah.
So if I open up a turtle file in Protege and then I work it, I close it, I save it, I get rid of Protege and I re-download Protege, I reopen it. Will it become a different file?
I don't think that is the case.
So it'll still be the same exact file, and then
Yeah,
if I
I
do
think that
anything-
has to do with the catalog file that pulls this stuff together.
okay.
Yeah. So there's some stability built in. Yeah. Let me move on. Disjointness, our old friend. SROYQ. A and B are disjoint just in case they share nothing in common. Easy peasy. Look at that. There they are. This is familiar, right? Transitivity. If X is related to Y, Y is related to Z, X is related to Z. Just like that. Boom. Symmetry. X is related to Y, Y is related to X. I wish loves worked like this, but you know, whatever. Asymmetry. If X is related to Y, Y is not related to X. Boom. Not going to happen. Loves often works that way. Reflexivity. My old enemy. Everything in the domain is related to itself under any relation. So, like that. Stupid. I hate it. Don't use it. Stay away from it. Irreflexivity. A little more interesting. Nothing in the domain under this relation is related to itself. If you're thinking of examples, some examples. Irreflexivity. Nothing is taller than itself. Everything's exactly as tall as itself. And that is the end of the lecture. Allen interval relations. Okay, it's a very common way to try to represent time. There's like a formal semantics around it in first order logic. It represents intervals, right? And the relationships among them, there are only a few, like interval before another interval, meets other intervals, overlaps by, started by, etc. Sometimes you'll come across, not infrequently, you'll come across people writing in OWL documentation, and they'll say, we can represent Allen interval algebra. No, you can't. OWL is not expressive enough to do that because you can't combine the appropriate role constraints and the same object properties to represent befores and meets and stuff. For example, befores is irreflexive and transitive. That would lead to a non-simple role chain in OWL, so you can't do it. If you try to, you'll get an error. Most implementations, though, at least assert before is transitive. Ontologies representing Allen interval relations are likely susceptible in this. I was giving a lecture about injection attacks on before, namely by asserting things like T1 is before T1. Because most of them don't even use these OWL constraints, actually. If you asserted, though, on equals, one of Allen's relations, that it's reflexive, is plausibly reflexive. Now to asserting this of an object property applies globally. If I put, for instance, right here, these screenshots from Protege, equals reflexive, that means these are inferences. That's why they're in yellow. They fell out of the reasoner. That means equals applies to everything in the domain. And these entities you're seeing over here, affected area 2, 4D trajectory forecast, those are all in the domain. Those are instances in the domain of this ontology that I was building. Equals is supposed to hold between intervals, not forecasts, but it applies to everything. Now, if you restrict the domain and range of interval equals, that will not help. If you restrict it to time, for instance, then that just means every instance follows, or every instance in the ontology now becomes an instance of time. Because our reasoners are conformist driven. They try to align what you said in the most plausible way they understand. They try to, so it would just entail if you put this domain and range restriction and reflexivity of equals, that everything is time. Equals is not reflexive in this case, but it has domain and range time. This is fine. Like this is what you should get. But if you put equals is reflexive and has domain and range time, this is everything in the domain, including affected areas and forecasts. It entails, for instance, that things like thunderstorms are equal to themselves and spatial regions are equal to themselves, even though it's about intervals. Man, I go on here to talk about how you can ruin somebody's day with swirl rules if you inject things like that, but that's for a later time. But yeah, roughly speaking, the semantics for reflexivity applies across the whole domain, no matter what object property you apply it to, because it's stupid. Somebody just asked why. Because it's stupid. I have no idea why they chose that. I have, like, as a logician, I have no idea. I've tried my best to think about why anybody would do that. I have no idea why they would do that.